Hi, and welcome to this research survey on security and privacy preservation in IoT-based E-health systems, its recent policies and methods. The objective of this survey is to provide an overview of the recent researches related to the preservation of security and privacy for healthcare data in Internet-based applications, based on some papers published in the last month. This presentation will be organized as you can see in slide. In section 2, we'll provide a review of some security considerations and a comparative analysis of efficient architecture models and access control algorithms. In section 3, we'll describe the challenges in developing practical privacy-preserving analytics in healthcare information systems. Last but not least, in section 4, we'll see in detail 3 recent studies that will serve as a sample of the current proposals and future lines of investigation for privacy and security preservation. IoT is currently applied to a high variety of applications as the healthcare applications, interconnecting all the available medical resources and providing reliable and effective smart health services. We all understand that health data must be protected while they are stored or in use, and that users will be more willing to use these kind of applications if they really trust that their personal and sensitive health data is going to be kept private and secure. Recognized authors in this subject are also aware that concerns of security and privacy haven't been well addressed in the past, and therefore they are focusing their efforts in innovative solutions and new methods like the ones we have selected for our survey. The following slides are summarizing the most suitable architecture models and access control algorithms in IoT-based e-health systems. Considering that the architecture is one of the major design constraints, the available models are categorized into 2 different types: distributed and cloud-based architectures. On the one hand, distributed architectures are the one consisting of a set of servers with different functionalities connected. They are very appropriated for clinical and hospital management systems. However, this model is not recommended for real-time monitoring systems and for dealing with large amounts of data, as in this case, its performance is affected. On the other hand, cloud-based architectures, where a cloud server provider is in charge of providing all the services across the cloud computing environment, is shown as the most suitable solution for the IoT-based e-health systems, as it can handle efficiently large and complex e-health records while imposing the required access policies to the data. Regarding the access control algorithms, a comparison among the most typical use mechanisms is summarized in the table, according to the level achieved for stated properties. Based on these results, as you can see, the ciphertext policy ABE arises as the most appropriate model for IoT-based e-health systems, as its performance is not affecting privacy and security, and thus it is computationally secure. Other use algorithms, on the other hand, are inappropriated for IoT-based e-health systems because they can lead to unauthorized data access or can be computationally inefficient. As conclusion, as it has been highlighted at the end of the slide, the combination of the cloud-based architecture with ciphertext ABE access control technique is the most suitable solution for data security and privacy concerns across IoT-based e-health systems currently. The practical privacy-preserving analytics based on the different application scenarios is described in the following slides. These application scenarios can be usually divided into 2 main categories: outsourced computation and information sharing. Outsourced computation, understood as the services provided by cloud computing, involves all data treatment from storage, analysis, communication, and any other intermediate phase. For protecting privacy in this kind of scenarios, 2 subcategories should be taken into account, as you can see here, depending on the confidence in the involved parties. a trusted service provider outsourcing to a honest but curious cloud provider, and users outsourcing to a honest but curious service provider. In the first scenario, the service provider is fully trusted, for instance, a university or a government entity. The cloud provider, however, is assumed honest but curious, what implies that all data needs to be encrypted before its submission to the cloud. The second scenario, however, are faced when the service provider cannot be trusted, and therefore it should be considered as honest but curious party. In this case, researchers have proposed to introduce a new element, the cryptography service provider, that will manage secret keys, decrypt intermediate results, and will assist the service provider. The main methods for privacy preserving are represented in the orange boxes, although their details are out of scope for this presentation as we have very limited time. We have included for your reference, however, the best identified schemes for each option, as well as their pros and cons. The other mentioned category in application scenarios is the called information sharing, that allows users to share their data with trusted and semi-trusted parties that can be researchers or medical providers, insurance companies, etc. We can consider there are three different approaches in this case. Interactive sharing, that is the case when service provider provides an interface to submit statistical queries. The non-interactive sharing that applies when the service provider publishes data while preserving users' identities so interested researchers can explore it. And finally, the collaborative manner, when multiple service providers generate models from combined or shared data without revealing the raw private data. Considering the three of them, the most accepted method for protecting privacy with the best trade-off for information sharing is the perturbation of the sensitive data, called differential privacy. As conclusion, as it is highlighted at the end of the slide again, for a well balance of cost of computation, communication, and storage in the healthcare frameworks, experts mainly recommend the use of data perturbation, both in outsourced computation and information sharing. We present now three solutions based on these described techniques that have been published recently by very renowned authors in the subject, aiming to address the security risks of healthcare data in internet-based applications. The first one is the signal scrambling method to secure data storage for healthcare applications. This method, in a nutshell, consists of an add-on security mechanism in the application layer, where a tiny part of the original healthcare record is used to scramble the remaining record. This can be a random number or even a piece of the record data itself that is kept locally for data retrieval, while the scrambled data, on the other hand, is sent for cloud storage, as we can see in the figure. The tiny piece of data that is preserved by authorized parties and used both for scrambling and descrambling the sensitive data, so that way they avoid any unauthorized access in the remote server. Several security experiments have proven the following security advantages. This model is developed at the application layer and can be built upon any existing security mechanism or communication protocol. It is also highly secure. If any attacker could get the scrambled data, as he won't have the tiny data for the scrambling, the brute force attack is unfeasible. This method has no effect on real-time management, and it is providing a very good performance too. And also, this method can be applied to high-dimensional data such as images. The second selected proposal is another promising solution presented recently. The policy hidden attribute-based access control protocol applied to smart health. Considering as we have seen before that the ciphertext policy ABE is one of the most appropriate solutions, the authors have presented PASH, a privacy-aware smart health access control system where the attribute values of access policies are hidden, and are hidden in encrypted records, and only the attributes names are revealed. Basically, the system architecture of PaaS consists of 4 algorithms for every of the existing phases. In phase 1, initialization, the public parameters and the master key are generated. In second phase, authorization, the access rights to data users and owners are provided. Then, during the third phase, the access policy to encrypt the record is defined, and then it is outsourced to the cloud, keeping it partially hidden. In final phase, the user recovers an encrypted record and uses the secret key to check if her attributes match the access policy, and in that case, decrypts the record. With this method, the authors have tried to solve the most important issues to ensure the secure and efficient applications in smart health, coming to the following conclusions. Regarding policy hidden in proposed PaaS method, the sensitive attribute in access policies are hidden from the public and even from the service provider, and only generic attribute names are sent. PaaS also provides an improvement regarding the decryption test. That is the testing done to determine if the user attributes satisfy the access policy of a ciphertext before the full decryption, by adding, in this case, a decryption test before the full decryption. Regarding large universe, PaaS doesn't impose any limitation on the attribute universe and provides a large universe construction without limiting the expressiveness of the policies. And finally, talking about expressiveness and full security, PaaS is more expressive and it is proven the full security in the standard model. Considering all these benefits, we can conclude that PaaS is highly appropriated for data security and privacy protection in e-health. The third selected proposal is a privacy-preserving fusion of IoT and big data for e-health, presented very recently, and focused on the fusion of IoT, big data, and cloud storage in the e-health application scenarios. In general lines, all records will be encrypted using the ABE methodology to perform the access control, while an authenticated key distribution procedure has been designed for the medical IoT network. A batch authenticating verification algorithm is also proposed to verify the source of encrypted IoT messages, and a new keyword match-based access policy has been built to update the commonly used mechanism to realize the policy updating control. This method also proves that the following functional and security requirements are guaranteed: patient, user, and medical node anonymity and traceability, confidentiality of the IoT key, authentication of the IoT key distribution, confidentiality and authentication of IoT messages, and also security against replay attacks. The proposed system is composed mainly of 13 algorithms divided in 4 phases, achieving the fusion of medical IoT and big data system. We can see here graphically the identified 4 phases, where the 13 algorithms comes into play. Phase 1, setup and registration, involves the use of the global setup, the patient, user, and medical node registration. In phase 2, e-health IoT key generation and IoT key extraction algorithms are run, as we can see in the figure on the right. In phase 3, IoT message encryption, message verification and decryption, the batch verification, and e-health records encryption and decryption algorithms are executed. And finally, in phase 4, keyword match-based policy update query and the keyword match-based ciphertext policy update algorithms are executed, completing the process. In this survey, we have tried to provide an overview of the recent methods and proposals for security and privacy preservation in IoT-based e-health systems, while providing a comparative analysis of different architecture elements, security measures, and techniques published over the last few months. We have presented the current state-of-the-art in security and privacy challenges, as well as some efficient architecture models and access control algorithms broadly accepted in these systems. We have also provided the differences in application scenarios for a practical privacy-preserving methodology. And finally, we have offered 3 innovative approaches aiming to deal with the described security and privacy challenges in IoT-based E-health systems. Hope you found it interesting, and I'll be glad to answer all the questions you may have or to go in depth in any of the sections presented here. So please contact me at the email address you are seeing here in slide. Thank you for your attention and see you next time.